Here comes Cosmo, coming to learn principles of formation evaluation. How are you doing, Cosmo? Do you know about shaly sandstones? Do you know about permeability, effective porosity? You know the differences? This dog is very smart, and I'm sure he can learn principles of formation evaluation. So today we have a beautiful, beautiful day here in the gorgeous Texas Hill Country. And it's so beautiful that it merits to be outside. That's the reason why Cosmo is here, who's coming here also to learn principles of formation evaluation. What do you think, Cosmo? Are we going to learn good things today? What do you think? Do you like petrophysics? Do you like formation evaluation? What do you think, man? Let's do it, huh? Let's do it. Hello again. I just wanted to introduce this exercise by reminding you that the well logs that we're about to see and work with are part of the compendium part 2, pages 1 to 3. We have all the handouts already on Canvas. Please bring them out, print them out, and follow me because everything is detailed there. I'm just going to add voice and pen to follow the mechanics of the process. And the process is precisely the same process that I described in extreme detail in the previous video. So just please follow me. And again, all the equations are carefully derived, explained for you in the textbook and also in the compendium. And please, when you have a chance, go ahead and look at the examples that I have at the very end of the compendium. They are beautiful, well explained, complete, and they have a step-by-step analysis of the interpretation method. With all that said, okay, let's go to the document camera now. Good. Okay, ladies and gentlemen, here we are with the example that we're going to be working with. This is the example which is in pages 1 to 3 of the compendium part 2. But if you remember, we also had this printed out in full color with all the logs together. This is a handout that I gave you at the very beginning of our course. So please try to undust it, get it out. It's this example that we have been using offshore Gulf of Mexico. It's a textbook example. That's the reason why I use it for so many things. Okay, so what are we going to be doing today? Today we're going to choose 2 points for analysis. And those 2 points for analysis are going to be located in the shaliest part of the log, right there, which is where we have a situation where it's the most interesting place where we have the shaliest part of the log. We can see that because of the gamma ray log. Also, we see low values of resistivity. Likewise, we see a decreased crossover neutron density here, and actually disappearing crossover right here, even though we have hydrocarbons. So if you were to apply Archie's equation here in this area, it will not work. So we have to make corrections, and the corrections are by, in this example, the assumption is that all of these shales present across this sedimentary unit, they're all laminated. And that makes a lot of sense because this is a turbidite sedimentary environment. And that's the reason why we have to do this analysis. And just to remind you, I'm going to show you a photograph of a turbidite sedimentary environment, which is on page 185. So it's very important very, very important to have a clear indication of what we're looking at here, because these are the rocks that we're going to be analyzing. These are not synthetic cases. This is a real case, but I just want you to take note of this, because here we have some layers of shale interspersed with layers of sandstone. When the volumetric concentration of shale increases, then the gamma ray log increases. If most of these layers were sandstone, then we could still use Archie's equation. But because we have a fair amount of shale present here, then we have to make corrections for the laminations of shale. So please remember this very important element of the sequence. Now here we are. So to designate points here, what we have to do first is to record the point. So for the sake of following all of these, I have the handout. And the handout, you can get it from Canvas. And that's the handout that I posted. You can follow it. All the elements are there. So what we're going to do is we are going to concentrate on two locations. In fact, we're probably going to have time to do one, but I just wanted to show you what the mechanics is for the calculation. So the first place where we want to make calculations is at 5,522. 5,522 feet measured depth. And that is located with this local minimum of the gamma ray log. Let me do the zoom right here. And that value is 5,522. 5,502 feet measured depth. If you go across this value, you are going to find out that this coincides with a local maximum of the resistivity log, and we also know that this coincides with the separation of neutron and density logs. With this separation compared to the separation we see below, it's a little bit smaller because of the presence of shale. That's one point. The second point that we're going to look at, this first point, we're going to locate sandstone number 1. That's the designation that I have in the handout. Now we're going to look at now at sandstone number 2, which is at 5,478. 5,478. And that's this local minimum right here for 478. This local minimum right here, that if you go across, it will be this value of resistivity, and if you go across the neutron and density logs, we will have this value of neutron and density logs. So this point is very interesting, even more so than the one below that we chose. This is the point number 2, and it's interesting because number 1, the volumetric concentration of shale is higher than in the first case. Second, the resistivity is much lower. And third, the crossover neutron density is non-existent. So what we're going to do is we're going to make corrections for analyzing. And our task for these 2 points is to calculate the sandstone porosity, which is the porosity of the interbedded sandstone layers. We are going to calculate the hydrocarbon pore volume. And of course, to calculate the hydrocarbon pore volume, we're going to have to calculate SW, and also to calculate those properties. Previously, we have to calculate CSH, volumetric concentration of shale, all of those. And to calculate SW, as I described in the PowerPoint presentation, before doing that, we have to calculate RW. And so we're going to have to go to the water saturated portion of the well to be able to calculate RW. And the second point that I want to make here, which is very important, is that to follow with this technique, we have to find a place where we have a pure shale. And again, the pure shale has to be designated such that the properties of that pure shell have to be the same properties of the interbedded shale layers that we have in this shale-laminated sandstone. And there are several possibilities. I want to point out that the evidence here in this example indicates that we have almost two types of shale. One type of shale goes above this point here, above this point, because we have a nice break in the properties of the logs. You can see that the neutron and density logs come like railroad tracks here, and suddenly the railroad tracks are moved over here. So there's something happened there similarly with the gamma ray log and with the resistivity. So here is a break in the sedimentary sequence. So we have to make sure that by no means we choose a shale, pure shale point above that break, because that shale is no longer genetically related to the shales that we have in the zone that we have for inspection. The second thing that we do is we have to go all over the place, because the shale point has to be consistent with everything we have here. And at the bottom of this log, we also have the same shale sequence right here. So for the purpose of this exercise, and because of the analysis that we have done, and I'm going to choose a point in this lower section, and the pure shale point is going to be located at 5,780 feet measured depth. Why that point? Well, if you look at this point, it will have exactly the same properties as above. We have a good local maximum. We have also a good separation, maximum separation between neutron and density logs. So here, the separation over here is what I usually call the capital D. Once again, you could have chosen the one up there, and you will get the same result. But the sandstone development that we have here is all connected, so the shale properties that we have at the bottom are genetically related to the properties of the shale we have at the top, and this comes from geological evidence. So any other shale layer that we have here, including the prominent one that we have at 5,650 or 45 right here, that also has the same properties. But we cannot choose this shale layer as reference for the pure shale because it's too thin, and some of the logs are affected by the thickness of that shell. So definitely we don't want to take that. We need a shell that is taking off so that the well logs across that shell are not affected by the bed thickness. So that's important. All right, so what do we do first? Once we have decided what is a pure shell, please take note of the following. We are going to look at the properties of the shell, and those properties are going to be propagated through the analysis. So it's very important to that selection. So what we have to do now here, once that we have selected that this is the point, what we have to do is to write down the values. The gamma ray log of the shell. We also have to write down the electrical resistivity of the shell. We have to note down the neutron porosity log in the shell. And we also have to write down the density porosity log in the shell. Maybe I didn't write this properly. It should have been written N, shell, like that. That's the same designation that I have in the PowerPoint and also in the book in case you want to follow it. So we have to read all of these values, and these values are going to constitute the basis of the analysis. All right, so if you look at the handout, those values are as follows here. Let me just write them down here for you by repeating. The gamma ray log at the pure shell is equal to 94 GAPI units. You can just go and read that. Then the density porosity in the pure shell is equal to 26.5%, and this is in sandstone porosity unit. So that's the right unit for this analysis because we're in the context of a clastic sedimentary sequence. So that's an important matrix choice. And now we go and read the neutron log at that sequence, and that's going to be 45.0% sandstone porosity units. The difference between these two is what I usually call the capital D. That's the difference between those two. And the other thing that we read is the electrical resistivity of the shell, and that electrical resistivity of the shell is 0.9 ohmmeters. This is important that you get familiar with these parameters. These are going to be the shell readings. Once we found and designated which one is the pure shell, those are going to be the basis of the analysis. So that's an important thing. So the next thing here that we have to do is to, for the purpose of the end member of the sequence, is to find a clean water saturated sandstone. This is going to be also the basis of the analysis, but why do we need a clean water saturated sandstone? Well, because when you're in the water saturated section, we can easily cross-verify that is clean if the neutron and density logs overlap in that particular segment. And that's going to be the basis for the gamma sand that we need for the calculation of CSH. That's an important one. Okay, so if you go down this example here, that's the location of the shell, and that's where we obtain the readings that I just plotted right here. Okay, now this, if we go up there, this section that you see over here is the section that is water saturated, more specifically brine saturated. So what we have to do is we have to focus on a local minimum of the gamma ray log, one local minimum, and it has to be such that if the at that point, if the sandstone is clean, shell free, then we have to have an overlap between the neutron and density logs. So what I'm going to choose as the location for this analysis will be at 5,681 feet measure depth. That's what the handout says. And why am I choosing that? Because if you go to that value, that will be precisely this point. Let me actually zoom into here so that you can see it better. And 5,681, it's right here, this local minimum right there. And if you go across, then we can also read the resistivity log at about that point. And if you go across, you are going to verify that both neutron and density logs overlap if you run a horizontal line across. So we have all the things that we know, that this is about one of the lowest values of gamma ray log, if not the lowest. In fact, there's a lower value of gamma ray log somewhere out here, but it's very close to this. And for verification purposes, then we know that at that point we also have a crossover in an overlap of neutron density logs, which verifies that that sandstone is clean. So for that value gamma ray log, anywhere on the log, we can rest assured that we are dealing with clean sandstones. That's our reference. So we're going to take the readings of that point now. So now we're ready to take the measurements at that particular local minimum, 5,681. We're ready to do that, and the readings are like falling in the water, saturated sandstone. And if you look at this carefully, it's a local minimum of gamma ray log is clean, shale free. When I say clean, I don't mean that you took a shower in the morning or brushed its teeth. No, it's just shale free. That's what I'm trying to say here. And what we have here now is, if you read the the density porosity, at that particular point, it reads 34.5% sandstone porosity units. And the density log reads exactly the same thing. So that's the value that we're looking at, the same values. And the other thing that I see here is that the electrical resistivity, RT, in the water zone is equal to 0.45 ohmmeters. That's what we want to read. Just so that you understand this, there were some students that had this problem of reading the resistivity logs. Please note that the lowest one is 0.2, so 0.3, 0.4, in 0.45 or 0.43, it will be okay in any way. All right, so now we have that. We have the shale properties. What we need to do now is we need to find the clean sandstone. For all practical purposes, this could be the clean sandstone, and it is a clean sandstone because the neutron and density logs overlap. But we could have used that as the basis of the gamma sandstone. But we recognize here in this analysis that the lowest value of gamma ray log that we have in this sequence takes place at 5,550, which is the point that I mentioned before, right here. The value of gamma ray log here will be the lowest one, and I'm going to call this the minimum value or the clean sandstone. We could have used the other one that we had before, but this is a little bit lower, so I will feel more comfortable dealing with a lower value. It really doesn't make much difference. But at that point, at 5,550 feet measured depth, we read that the gamma ray log minimum, that gamma ray log is 25 GAPI. So now we have that new measurement. And by the way, if you hear funny noises here, it's because Cosmo is here looking for a cookie. Cosmo, pay attention, man. You have to follow these calculations. Not all the time you're going to get your cookies, so follow me. And now with this development, now we know that based on the analysis that I had in the PowerPoint presentation, we know that now CSH can, in this laminated sequence, can be calculated from the gamma ray log minus the gamma ray log in the pure shell divided by the difference between the gamma ray log in the pure shell with respect to the gamma ray log in the clean sandstone. So that's what we have. In this example, we can do this because we do have a clean sandstone, so we can operate with that analysis. However, if you recall the previous exercise that we did, which is on page 11, and just for comparison, and on page 11, which is also a turbidite sedimentary sequence in the deep water Gulf of Mexico, the minimum value gamma ray log that we had there in the water saturated sandstone, did not produce overlap between neutron and density logs, and therefore that will be the lowercase d. And to calculate the volumetric concentration of shale with respect to the gamma ray log, we cannot start from 0 for the gamma ray log for a clean sandstone. We cannot, because we don't have a clean sandstone. So in cases like that, what we have to do is stay in the water saturated sandstone and measure the lowest value of gamma ray log that we have there, analyze the separation between neutron density logs, measure that as a lowercase d, and compare that to the uppercase D, which is the separation between neutron and density logs in the point that we chose to be the pure shale. So that will be the, and so that value for that particular value of gamma ray log, now we know what the volumetric concentration of shale is, and that gives us a reference point to build the linear relationship between gamma ray log and volumetric concentration of shale. All right, so now that we had that little digression here, let's return to sandstone 1 and sandstone 2. Those are the ones that we designated before, and those are the places where we need to do the calculation of all the storage properties. It's a hydrocarbon, those are hydrocarbon bearing sandstones. I described them before. If you look at that, you're going to see that the gamma ray log in number 1, if you read it, it will be 46 GAPI. And in the second one, the gamma ray log here will be 62 GAPIs. All right. Now let's take note of the other values. The density porosity log in the first one is going to be equal to 39% sandstone porosity units, and the neutron log is equal to 23.5 porosity units sandstone, and the electrical resistivity here, RT, is equal to 2.8 ohmmeters. All right, and then for sandstone 2, just to repeat the calculations, we have 62 GAPIs, and the density porosity log here is equal to 26.5% sandstone, and the neutron log here is equal to 32.0% sandstone porosity units, and RT is equal to 1.5 ohmmeters. What I want to point out is that these are very, very low values of resistivity, as I indicated before. If you are naive and you have not taken this class, and if you substitute those values in Archie's equation without having corrected for the presence of shale, immediately you will get a ton of water. And then, because you were naive, you would say there's no hydrocarbons here. And that's not true. What we have to do is to correct them. I also want to point out here in that this sandstone number 1, the neutron log is lower than the density log. So that is already telling us that we have a light fluid, despite the fact that it hasn't been corrected. But in this case, it's the opposite. The neutron log is larger than the density log. So in this example, you might get happy here. In this example here, you might get a little bit unsettled. But I'm going to show you that when you make the corrections, in both cases, the neutron log, when corrected for the presence of shale, will be invariably lower than the density log corrected for shale, and that will unmask the effect of the presence of light. So if you continue with the calculations for sandstone number 1 and sandstone number 2, here Let me actually retrieve the zoom so that I can do more. Then here we can calculate CSH again by doing gamma minus gamma sand over gamma shale minus gamma sand. As I was writing this equation here, I just realized that in the upper part which I wrote, this formula is incorrect. This should be gamma sand. Sorry. You know, this is what happens when you don't have in front of you 80 students that are happy and eager to correct you. And you know, one is an old dog, just like Cosmo, and one is prone to making mistakes. But luckily I realized, so let me go back, and that will be sandstone. Okay, thank you. Sorry for that. And now I'm going back to the equation here, and we're going to calculate the volumetric concentration of shale right here. And if you do that analysis, essentially what you find is that for this sandstone number 1, then this comes to be 46, which is the gamma ray log, minus the 25 that we have in the clean sandstone, and we have the 94 minus 25, which is what we have for minimum, and this, if you calculate, will give you 34.43%. That means that in that volume of investigation of the measurement, 30% of the rock is shale, and 70% is of the remaining part is sandstone. So now what happens with the second one? In the second one, CSH here, it's going to be equal to the gamma ray log, which is in this case is 62, and then minus the 25, and over 94 minus 25, and the result of this calculation is 53.62%. So what's going on here? Well, what's going on here is that in this sandstone number 2, more than 50% of the rock is shale. How about that? Most people would discard this segment just because on the basis of the net to gross being so small. But wait, don't discard it until we know that the intervening layers of sandstone have good storage and flow properties. Moving on with these calculations, now what I'm going to do now is to calculate the sandstone porosity, that is to say the porosity of the intervening layers of sandstone. And to do that, what we have to do is, as I indicated in the PowerPoint, is to do the corrections for the presence of shale. And those corrections are as follows. We take the density log corrected is equal to the original density log minus CSH times the density porosity log in a pure shell, and that divided by 1 minus CSH. So if you do that calculation, and then we have to do the same thing for the neutron log, corrected equals neutron log minus CSH neutron pure shell, and 1 minus CSH. Just to remind you, these values are the value of the density log in a pure shell, and this is the value of the neutron log and the pure shell. This is the reading of the density log in the sandstone that we're inspecting. This is the reading of the neutron log, and this is the previously calculated value of volumetric concentration of shale. So for this sandstone number 1, you go ahead and do the calculations, and this is going to be 39 or 0.39 minus CSH that we just calculated, which is 0.3043 here, times the density log in the pure shell, which we calculated before to be 0.26 0.265. That's what we did. Just to remind you, this 0.265 comes from the readings that we did in the pure shale right here. All right, and then we divide all of these by 1 minus CSH, which again is 0.3043. And what you find here is that the density corrected log for presence of shale is approximately 44.47%. Okay, now we are going to do the same thing for the neutron log. And to do the correction, again, let me introduce the values, which is the neutron log for this sandstone is 0.235, and then the volumetric concentration of shale is 0.3043, and the neutron log in a pure shale is 0.45 based on the calculations that we did before, and 1 minus CSH is 0.3043. So if you do the calculations here, you are going to find that these calculations are going to give you 14.09. When we were in class, I had my dream team of calculators, and that was Mr. Jimenez and some of the other students that were so nice, sitting at the front and always eager and willing to do the calculations. But now I don't have my dream team, so I just have to do it by myself. By the way, hope Mr. Jimenez is doing fine. So what do we see? Look at that. This and this. If you compare the difference between the neutron and the density logs after correction, you are going to see that the difference has increased with respect to the difference that we had before making the corrections. What does that mean? It means that that difference here, we had that difference before correction. When you make the correction, the difference extends. So that means that we're actually effectively taking away the masking effect of the shale. In this process, the crossover increases and it becomes somewhat closer to the crossover that we have in the clean sandstone. That's what we have seen. If you take the same procedure, I'm running out of space here, but if you apply the same idea to the second sandstone, you apply, please do it, it's in the handouts. This is what you're going to find out. Of course, we have 53%, 53.62%. But if you do the analysis, you're going to find that in that particular case, the density corrected log becomes 26.5%, 26.5%. Whereas the neutron corrected log, if you do the same process in that sandstone number 2, it becomes 16.97. How about that? And that's a very interesting thing, because look, before we did the correction, just to remind you, the values of neutron and density log before correction were 26.5 for the density log, and they were 32% for the neutron log. So now what we have here is a situation where the correction has given us such that the neutron corrected log is now smaller than the density corrected log. I want you to see this very important fact here, that sandstone is right here, and look, there's no crossover at the beginning between neutron and density logs. We make the correction and suddenly the neutron log is now smaller than the density log, which means that if I had a yellow color here and plotted the corrected neutron density logs, then the yellow highlighted will extend all the way up to here, you see? So, in consequence, this correction, the correction that we apply to the neutron and density logs, is the one that has the purpose of eliminating the effect, the masking effect that the shale layers have in this process. Okay, so what do we do now? Now that we have this condition that the neutron corrected is smaller than the density corrected in both cases, and of course we're very happy here. If that were not the case, that would mean that we did something wrong. But as a consequence of that, now we can approximate the sandstone porosity. We can approximate it as the square root of the average of the density corrected square and the neutron corrected square and divided by 2, similar to what we did for the clean sandstone. You see, once you have taken out the masking effect of the shells, the intervening shells, then everything works out just in the same way we did it in class for the clean sandstone. So if you apply that criteria here, again, we're very happy here. We're probably drilling because now the neutron and density. So if you apply the same procedure for the other sandstone, you're going to find out that this process for sandstone number 2 is going to give you 22.25%. That is the square root of the average of the corrected squares of neutron and density logs. That's what it has. That's for sandstone number 2. And for if you do that process for sandstone number 1, you are going to find out that that is going to give you approximately 32.98. That's about 33. Okay, so for sandstone, this is, sorry, it's a little bit messy here, but this is for sandstone number 1, and this is what we find for sandstone number 2. So what do we see? Well, the place where sandstone number 2 is, porosity is not negligible. It's 22.25%, but it's a little bit lower than the sandstone porosity that we find at the first location, which is 32.98. And the second point that I want to emphasize here is that, look, when we find this value of porosity in the sandstone number 1, this value of porosity is actually very close to the value of porosity that we have in the clean sandstone right here. So that means that those sandstones that we have in the highly laminated section of the well here, they don't have negligible porosity, so we can use them for good storage. How about that? Okay, so now we have for sandstone number 1 and sandstone number 2 here, we had calculated CSH, both of them. We have calculated the sandstone porosity for both of them. We're in good shape. What else do we need to do? Well, we need to calculate hydrocarbon saturation in the layers of sandstone, the intervening layers of sandstone. So how are we going to do that? Well, what we have to do is we have to take the electrical resistivity measure and think that this one comes, as I indicated in the PowerPoint, from a parallel circuit that has the resistivity of the shell and the resistivity of the sandstone over here. And we know the resistivity of the shell, we know the measured resistivity, and we know the proportions of these two. So we are going to unravel our sand. In other words, this is what we're going to do. We are going to take the value, the circuit, and we know that this is going to be CSH divided by RSH, plus 1 minus CSH divided by dr sandstone. And that applies to the two sandstones. So what we have to do now is, this is the measurement, this is the resistivity of the shell, and this is CSH. So what we have to do is to solve this equation for our sand. And then from that R sand, we are going to find it in both cases. And as a consequence, now we're one step closer to the calculation of the saturation. And just to remind you, the calculation of that will give you something that looks if you solve all of these, I hope you remember that in the PowerPoint we had 1 minus CSH, and the other factor that we need to multiply was R T times R shell, and then here we had R shell minus CSH times RT. That was the formula we had in the PowerPoint, and it was very important to make sure that this denominator was not zero and it was always positive. So if you do that calculation for sandstone number 1, you're going to find that the resistivity of the sand turns out to be 36.55 ohmmeters. Just to remind you, the resistivity, the measured resistivity was, the RT was, for this example, 2.8 ohmmeters. Now, if you do the same analysis, the same calculation for the second sandstone, using the same formula, you're going to find that the resistivity of the sandstone in this particular example will give you about 6.54 ohmmeters for an initial value of RT that was 1.5 ohmmeters. All right, what does it mean? In both cases, it means that once we make the correction for the parallel circuit, so we eliminate the conductive effect of the shells, then the RT increases. You see, it goes from low to high in both cases. And that's good, because the higher the sandstone resistivity, the lower the water saturation. So far, so good. And the second point that I want to make sure is that if you do the calculations properly, I have this in the handout, you're going to, first of all, verify that this denominator in both cases never gets to be negative. So we are in good shape. And now that we have the R sandstone, we can actually apply Arch's equation to calculate the water saturation. What do I say? Well, we have, according to Arch's equation, assuming that those intervening sandstones don't have any grain coating clay, what we can do is this formation factor, this is the sandstone, M, and then we multiply by 1 over SW to the N. And then from here, we of course know that SW becomes equal to RW divided by R sand multiplied by a formation factor of the sandstone layers, 1 over N. In this example, this handout, just to simplify matters, we have assumed that A equals 1, M equals 2, and N equals 2. That can be applied for the sandstone layers. So let's just, are we in a position now to calculate this? Let's see. We have the sandstone porosity that we calculated. We have the parameters. We have the sandstone resistivity. We just calculated that. What else do we need? RW. So how am I going to calculate RW? Well, similar to what we did before. We are going to go to the water saturated sandstone and we are going to implement Arch's equation there. And from the implementation of Arch's equation, we are going to calculate RW, that will be right here, which is where the water saturated sandstone is. I'm going to calculate it right here, and then I'm going to extrapolate it all the way to here. Please remember that when the extrapolation is shorter than 200 feet for a normal geothermal gradient, and even if you calculate it here, you don't need to make temperature corrections. But if the extrapolation is longer than that, then you have to start making corrections. And the second point that I'm going to make sure that I emphasize is that the salinity of formation water here, I'm assuming that is the same salinity of the formation water here, because I'm making the assumption that all of the intervening sandstones from the top to the bottom, all of them are hydraulically communicated. That's something that I need to verify with pressure points, pressure gradients, but I know that there's a very high possibility that that's the case, because in this reservoir we have a gravity segregated fluids, which at the top we have gas, then we have oil, and then we have water. So this segregation, gravity segregation of the fluids, is an indirect indication that all of the intervening sandstones here are hydraulically communicated. And just to remind you, in the water saturated sandstone, which we did here, we already know what the neutron and density logs are the same, and because they are the same, they overlap, that's the sandstone porosity, which is 34.5%. And in a case like this, we also have the electrical resistivity of the rock. So because of that, at that particular point, now we're in a position to apply Archie's equation. Let's assume that it's 100% water saturated. So we have the equation here, SW equals 0. So I'm sorry, SW equals 1. So we have now that RW equals RT, porosity of sandstone to the M, divided by A. And if you apply those equations, you're going to find that RW equals 0.0536 ohmmeters. So now we can take this value to the upper sandstones and proceed with the calculations. However, at this point I would like to make a parenthesis and bring back page 11 and show you something interesting. In this example, in the water saturated sandstone, we don't have a clean sandstone, and we know that it's not clean because the neutron and density logs do not overlap, and that lack of overlap is not negligible. It's significant, as I explained before. So what am I going to do here? Well, of course, what we have to do is we have to calculate CSH here, and in this example, and we have to correct the neutron and density logs for the presence of shaliness. And then we have to calculate the sandstone porosity here. See? The same thing that we applied in the previous example for the hydrocarbon sandstone, we have to do it here. We have to correct neutron and density logs for the presence of sandstone. When we correct them, they are going to be the same, and that will be the sandstone porosity. Now, that will be one part of the equation. But if you want to calculate RW, then this resistivity that you have here has to be corrected for the presence of shale. So again, you have to apply this circuit, parallel circuit, that says that you have CSH, RSH, plus 1 minus CSH divided by the RT. So it means that this equation that solves for R sand has to be also implemented in the water saturated sandstone. It gets a little bit cumbersome, it gets a little bit more complicated, but essentially whenever you have shaliness, be it in the water saturated sandstone or in the hydrocarbon saturated sandstone, you have to implement the parallel circuit analogy so that you estimate the R sand right here. you correct the porosities for the presence of shale, and once you get those, then you can apply Arch's equation here that says R sand equals RW, and then here you have the sandstone porosity to the M, and from here we can calculate the RW. So as I said, it just gets a little bit more cumbersome when even the water saturated sandstone is shaly, because we have to apply these corrections there too in order to be able to calculate. Okay, so now that we have RW, going back to the example, sorry for that digression, but it was a very important parenthesis. So now we have the RW that I calculated in the water saturated sandstone. I return to the hydrocarbon saturated sandstone, and now I'm in a condition to calculate water saturation. And then if you do this analysis, what you're going to find out is in sandstone 1, you are going to get that SW equals 11.61%. And in sandstone 2, you are going to find out that SW equals 59.31%. Okay, so what does it mean? What does it mean? Well, it means that in this upper sandstone you have more water than hydrocarbon. So if that is the case, then we can calculate hydrocarbon saturation, and for this case hydrocarbon saturation becomes 88.39%, and in this case it becomes in that case it becomes 59, in this example it was 40.69% is in the handout, so hydrocarbon saturation becomes 59.31%. So in sandstone number 1 we have more hydrocarbon saturation than in sandstone number 2. But now here comes a very important point. What is a hydrocarbon pore volume here? And to remind you, it's very important in clean sandstones, we know that that is a product of sandstone porosity times hydrocarbon saturation. That's what we have. But because that was in the case of clean sandstones, but now we're dealing with sandstone shale laminated sequence, so we have to take out the effect of the volumetric concentration of shale to properly account for the volume of sandstone that we have in a unit cube, and that's what we have to do here. Luckily we have this calculation, and we have previously calculated that volume. So if you do that calculation all the way through for sandstone number 1, you are going to find out that for sandstone number 1 the hydrocarbon pore volume is 20.28. And if you apply the same calculation for the second sandstone, you are going to find out that that is about 7.08%. What does it mean? It means that if you take a unit volume of rock, in this example 20% of that rock will be filled with hydrocarbons, and then here if you take a unit volume, 7% of that rock will be filled with hydrocarbons. So is that useful or not? Well, I don't think it's bad, because it's the same thing. It will be the same thing as having a rock that has 20% porosity, you see, full of hydrocarbon, or this a rock that has 7% porosity full of hydrocarbon. So that's how the volumes come about once we have taken out the effect of the presence of shale, so we only remain with the net to gross. To complete the analysis, the final step is to calculate the hydrocarbon density. That's important to know because we have to have an indication of what type of fluid we have here. I have to tell you that that indication is not so difficult to know here because, as I said before, this is a gravity segregated reservoir, and in the center of it we have oil, and then we have gas right here. So very likely all of this is going to be gas, or maybe gas and condensates, but mostly gas. So whatever happens is not possible unless we have a seal or something of that nature. There's not a possibility that with hydraulic communication we should have a fluid here that is heavier than this fluid below, and this fluid below is gas, so very likely this is going to be gas. So we don't need even to have pressure gradients here. It's very likely that that's going to be the situation, but regardless, we want to understand whether this is the case. So to do that, what we have to do is, going back to this equation, is we have to do it by steps, and those steps are as follows. First of all, we realize that the density of the rock at any one point in this example is a linear combination of the density of the shale with the volume concentration of the shale plus 1 minus CSH times the density of the sandstone, like this. This is a measurement that comes from the density porosity log. So we have that. And in the pure shale, we also have the density porosity log in the pure shale. So we have to apply the transformation that, since the logs are given in sandstone porosity units, I have to apply the transformation so that I get these values. Once I have those values, then I solve for the density of sandstone, and that is 1 over 1 minus CSH, open parentheses, the density of the rock, minus CSH, the density of the shale. Good, so far so good. And that will be the density of the sandstone, the density of the individual layers of sandstone in the sandwich of sandstone and shale. Second, I realize that the density of sandstone is equal to the porosity of the sandstone times the density of the fluid that I have in the sandstone plus 1 minus porosity of the sandstone times the density of the matrix. Because we are in a socioclastic sequence here, this density of the matrix would correspond to the density of quartz, which is 2.65 grams per cubic centimeter. And the density of the fluid, that's what we want to get. And the density of the sandstone, that's what we calculated before. And of course, the density of the sandstone here, the porosity of sandstone is what we calculated before, and the density of the sandstone comes from here. So if I solve that equation for the density of the fluid, then it becomes 1 over porosity of the sandstone, open parentheses, and I have the density of the sandstone minus 1 minus porosity of the sandstone, the density of the matrix, with everything I know. Of course, this is a concatenated calculation, but I'm doing this in sequence so that it's clear what I'm doing. I'm sure that there are easier ways to simplify the equations, but I'm not pursuing simplification here. I'm just pursuing the logic. So once I know the density of the fluid, here comes the last step, which is I know that this is a linear combination of the density of the part of water that I have here plus the part of hydrocarbon that I have here. And the density of water, this depends on the salinity and pressure and temperature, but in this example I'm going to make the assumption that is 1.0 grams per cubic centimeter. Of course, salinity will make it a little bit higher, and we have to be consistent with the salinity that we found in the calculation of RW. Just make sure that that salinity is consistent with here, but I'm not going to do that step. So consequently, the density of the hydrocarbon is going to be 1 over 1 minus SW, and now we have the density of the fluid minus SW times the density of the water. And this SW is the one that I calculated for that particular sandstone once I did all the corrections, and the density of the fluid is the one that I did before, and the SW is the one that I calculated. So that's how this is a little bit of a tortuous way to do things, but if you do the analysis, you are going to find out two very interesting things. That the density for sandstone number 1 the density of the hydrocarbon is 0.35 grams per cubic centimeter. Please follow the handout. Okay, and now for the second sandstone, you are going to find out that the density of the hydrocarbon is 0.46. And it really doesn't make sense that the higher one be lighter. Most likely, this calculation for the one that has the largest concentration of shale, because of all the corrections, probably this is only an approximation, but this value seems a little bit better correlated with the fact that we have gas. And I just have to say here that some students often ask me, how do I know that it's gas? Or how do I know that a given density is gas? If I go to Wikipedia or something, they said that this is more like a liquid hydrocarbon. And the answer is, it depends on the pressure and temperature. We know that the density of these fluids, because they're highly compressible, they depend on the temperature and pressure. As I said before, you can have gas and you put a lot of pressure, and it condenses into a liquid, sublimation. Likewise, if you have a light fluid and you release the pressure, then you reach the bubble point and it becomes gas. And at that point, the density decreases. So because of that, we have these transitions of fluids in their gas liquid state that depend on the pressure and temperature that they have, which in turn depends, their behavior depends on their compositions. So it's hard to say, but what I can tell you for sure is that this is gas because of the context. If I didn't have this context that I have here, or looking at this area, it would be impossible for me to tell you. If I just abstract myself from here and I tell you, well, we have a crossover, and what is that? Well, it would be very hard to know whether this is a liquid or a gas. But because I have the contextual information that here the fluids I have gas and then oil, most likely the fluids that I have here are gas because of gravity segregation. And the important thing of this calculation is verification. We do that. This is probably not the most accurate way to calculate hydrocarbon densities or fluid densities. The most reliable way is, of course, to acquire pressure points here and to calculate the pressure gradient. And from the pressure gradient, you calculate the fluid density. But this is an alternative way, cheaper, that allows you to verify your calculations and it gives you an indirect way to estimate those. With that, that concludes our analysis and calculations. I hope that you're happy. I hope that you followed me, and I hope that everything is clear. Sorry it took a long time. These lectures are taking much more time than I anticipated in the recording, more time than the time allotted to lectures in class, but I just try to be a little bit more, a little bit clearer, a little bit more specific, slower, so that the concepts are properly understood, and every once in a while I make comments here and there. But the homework that I just posted for due next week, the intent of that homework is to replicate these calculations for another case that we have in the compendium and also a synthetic case. So please complete those exercises, replicate the calculations, and we are going to be in good shape. Because the most important thing that I want you to take away from this exercise is the following: that in the beginning, because of the high values of gamma ray log, the low values of resistivity, and the lack of crossover, most people who are not qualified to do petrophysics or formation evaluation would have discarded this section as not useful. And this section, by the way, is interesting because it's in the lobe, the distal part with two radii systems, so it has a large volume compared to what you would have in a channel. So if you discard this area in terms of the presence of hydrocarbons, then you are actually discarding a large volume. But now that we know how to deal with this and how to eliminate the effective shell and how to assess whether the intervening layers of sandstone have or have not good storage, Now we can go back and analyze. And once again, in Texas, many reservoirs in Texas, Vicksburg Formation, Frio Formation, many of those were initially explored and exploited only along the sections where the porosity was extremely good and the mark of hydrocarbons was excellent. That was the best slice of the cake, so to speak. But if you go back, when people found those reservoirs, they completely discarded these other ones that were shaly just because they didn't have the good science, they didn't have the means of interpretation. So now one of the best businesses is actually to go back to those old wells where sections like these ones were discarded and do workovers because they have good quantities of hydrocarbon and probably have much better permeability than the permeability that you have in the Permian Basin. So if you find something like this, it would potentially be easier and cheaper to produce than a well in the Permian Basin. And of course, in this example, the well will decline much more slowly than in the case of the Permian Basin. So I hope you get this very important knowledge and you apply it. It's very useful and it's applied widely by oil companies. With that said, thank you so much. Stay healthy, be happy, have a nice weekend, and we'll come back with more examples of application next week. Have fun and goodbye. And here is my dog Cosmo after a session of recordings of formation evaluation. He's happy the recording is over, but he's exhausted, just like me, but happy, I guess. And he's learned a lot of things about formation evaluation just by listening to me talking and recording lectures once, twice, 3 times sometimes. And now he knows the concepts behind capillary pressure, relative permeability. He knows the difference between total porosity and effective porosity in the presence of grain coating clay. Great guy. Now taking a siesta, well-deserved siesta. How do you feel about that, Cosmo? Are you happy? You like it? Goodbye.